Hello everyone and welcome to this week's Seds Online webinar. We're really pleased to be able to offer all of our resources and webinars for free thanks to sponsorship from the International Association of Sedimentologists, the IAS. Dr. Miquel Moré joins us this week. We're really pleased to be able to welcome him. He undertook his bachelor's in geology and master's in geology at the University Autónoma of Barcelona, which he completed in 2009. Miquel's PhD was in stratigraphy and sedimentology, which he completed in 2013 at the University Autónoma of Barcelona. In 2013, he moved to the University of Manchester to join the Strat group, where he joined as a postdoctoral research associate. In 2017, he joined the University of Oslo in Norway as a postdoctoral research fellow, where he remains as a researcher in the Department of Geosciences. Miquel is working on classic depositional systems across different basin settings, and is today going to talk to us about Clinothem architecture and sediment distribution in exhumed basin margin successions. So it sounds fantastic, and I'm really looking forward to hearing what you have to say. So without further ado, we'll hand over to you, Miquel.
Thank you very much, Catherine. And thank you very much, Seds Online, for giving me the opportunity to be here today. Also, I wanted to personally thank what you guys are doing for the sedimentary geology community these days. And before I continue, I also wanted to thank all my collaborators, because they have done a lot as a fundamental part of this job. So it's not only me. So as an outline of the talk, first of all, I will introduce concepts of clinoforms and clinothems. What are the differences between the two and why it is important to study them. Then I will briefly introduce the study area in the Karoo Basin. Then I'll show a couple of case studies that will bring some discussion points into the presentation. Then I will potentially touch upon some other studies that we've done very briefly, and then finally concluding remarks and hopefully some useful take-home messages for all of you guys. So first things first, clinoforms and clinothems. So what we call clinoforms are basinward dipping and often sigmoidal shaped chronostratigraphic surfaces. So basically they are timelines. Whereas clinothems are the rock bodies that are contained between two of these clinoform surfaces. They are important because they are the fundamental building blocks of sedimentary basin margin successions. And here in the figure underneath, you can see that the three main components of clinothems: topsets, which are the normally shallow dipping upper part of clinothem; foreset, the intermediate and often steeper part of a clinothem; and then bottomset, which is the distal and also often shallow dipping part. So as you may know, clinothems occur at a variety of scales, from meter scale to, in mouth bars, for example, to hundreds of meters of scale in basin margin successions. And they, of course, receive several names, and I'm gonna try to stay away to the conflict of nomenclature, and I'm gonna try to keep it as easy as possible. So why do we care about clinoforms and clinothems? One of the reasons is because of clinoform trajectory analysis. This is a technique or a tool that complements system track analysis, which is classic from sequence stratigraphy. And it essentially tries to study the migration through time of sedimentary systems using different breaks in slope, what we call rollovers. For example, in this case, the shelf edge rollover is the inflection point between the topset shelf and the foreset, which is in this case the submarine slope. This technique is useful because it offers information about the balance between accommodation and sediment supply, and it's independent of aerostatic sea level variations. However, and this is where our research comes into play, there are some limitations of this technique. Like, for example, dominant process regime and lateral variability, for instance. So depending on what is the process dominating the shelf, we might have more delivery of sun to the bottom set or not. And we will touch upon this in the next few slides. So in order to bridge some of these limitations of the model, then we have outcrop examples. And outcrop examples allow us to study these clinothems in higher detail and in higher resolution than what seismic can achieve. And that is why we go to places like the Karoo Basin in South Africa. So some of you may know about the Karoo Basin. The Karoo Basin is located in the south of the African continent. And the Karoo Basin formed as a retroarc foreland basin as a consequence of the subduction of the Paleo-Pacific plate underneath the southwest margin of Gondwana. Other authors think that the basin started to form earlier as mantle flow and dynamic topography, but this is not the discussion that I want to bring today. So essentially, the important part that I want you guys to retain is that in the Karoo Basin, we have the Permian Eka group, which is a really nicely exposed shallowing upward succession. There are several formation names which are not important, but the important part is that here we have 2 kilometers of stratigraphy that is really well exposed and is showing a transition from mud-dominated basin floor deposits, basin floor sand-rich basin floor fans, channelized slope succession, and then shelf and eventually coastal plain and paralic deposits. So this basin and the exposures have allowed to do a lot of research over the last tens of years. Essentially, a lot of work has been done in the deep water succession and led essentially by the Strat group, led by Steve Flint and Dave Hodgson. And all these years of postdoc projects and papers have allowed us to have this really amazing data set and to reconstruct a basin margin along hundreds of kilometers of distance and thousands of meters of stratigraphy. And this really good sedimentary log data set is integrated with a few research boreholes. And with this, we can construct these correlation panels, but we can perform studies that range from very small scale, core scale observations all the way to basin margin reconstructions. So this is pretty outstanding and makes this basin quite unique. So two of the main areas of study are the Lanesborough Deposcenter and the Tankwa Deposcenter that I'm going to talk about a bit later. So this is how the rocks look like in the field. So this is the Gattisberg outcrop, which is located in the northern part of the Tankwa Deposcenter. And here you have about 500 meters of stratigraphy. You can see how well exposed the rocks are. Basin floor deposits at the bottom, log deposits in the middle part, and shelf deposits at the top. So this is an amazing place to work because exposure is fantastic. And of course, South Africa is a fantastic place to work. So now I'm going to talk about this first case study. And I'm going to introduce a few concepts first. So we know that clinoform studies are very common these days. We have several of them, both in outcrop and in subsurface. But most of our clinoform studies are still essentially based on depositional deep parallel sections. And this has its limitations because they rarely consider the along-strike variability of coeval, topset, foreset, and bottomset segments. And this is normally because of outcrop scale or because of limitations of data. These days, because we have 3D seismic cubes, we are getting better at documenting the lateral variability, but still the resolution at which we can achieve this is limited. Sorry. Another thing that we don't know, or that we don't know the reason for, is that several basin margins evolve from an early phase dominated by erosion and sediment bypass and deposition in the basin floor to a later phase where we have accretion and formation of Clinothems. So we don't know how these transitions occur. And we know that it happens in several basins. And basically the reason why this happens is not an easy answer to give, but we're gonna try to attempt this in the Karoo Basin. So again, this is the Lanesborough Deposcenter to the east of the study area. Again, I will remind you, basin floor fans, sand-rich, submarine slope deposits, and deltaic parasequences. And here we have several sedimentary logs that are integrating with mapping. And here we can reconstruct basin margin scale Clinothems. And in these clinothems, we can see the positions of several interfaces like the shelf edge rollover. So this is a correlation panel of the Lanesburg Depot Center. And here we can see very nicely how the basin floor and slope succession is dominated by these channels, levee deposits that are actually delivering a lot of sand into the basin floor. Whereas the upper part, the shelf, part of the succession, the waterfall formation, is an accretionary shelf that is storing a lot of sand in the shelf and very limited deposition in the slope. Right. So in between these two units, or these two parts of the succession, we have unit G. And this unit G is a very interesting unit that received limited attention. It's a thin-bedded dominated unit, and the outcrops are not very nice. And it was used as a datum, as a top datum by the studies of the underlying stratigraphy and as a bottom datum for the studies of the overlying stratigraphy. But it sits in a very interesting position because it's basically recording the transition from this erosion-dominated, bypass-dominated margin to this accretion-dominated margin. So our objectives were to study the down dip and across-strike variability of this unit, and then try to link the observations to this transition. So this is a map of the Lanesburg Depot Center. See, here you can see, sorry. Here you can see the distribution of the outcrop belt in light gray. So unit G is exposed along the post-depositional west and east trending synclines and anticlines. And this is allowing us to study almost three-dimensionally the distribution of this unit. So the data set includes 150 thickness points, which are the black dots, 23 detailed sedimentary sections, which are the red dots, and then this is complemented by a few polycurrent readings and some drone topography. So when we try to map the, or to try to plot the polycurrent map, we have the unidirectional polycurrent readings, which are the blue ones. They point towards an east-northeast direction. And this is consistent with the previous studies that have suggested that the distal part of the basin is located to the east and northeast. And interestingly, all the bidirectional values are located in the southwest. And this is therefore where we predict to have the shallower deposits of this unit. And then what we did was also to plot the thicknesses of the underlying units and the overlying units. Here you can see that the thickness of the underlying unit suggests that there was a complex thickness distribution that we associate to complex seabed topography. Whereas in the upper part, we have that the thickness distribution is much more consistent with a thickening and then thinning. Unit G is here in the middle. So here, this is the thickness distribution. And where, as you can see, there is a similar or is a hybrid distribution between the map at the bottom and the map above. And when we try to translate this to what we think this is showing, is basically a thickening then thinning pattern that we suggest that is basically showing a development of a Clinothem succession. So from unit G and prograding over the next units. So this was our hypothesis. So the first hypothesis with the thickness maps were that unit G was the start of the development of these Clinothems. And then we moved on, and then we wanted to look at the deposits of unit G. So this is a fence correlation panel of unit G in the Lanesburg Depot Center. So here you can see 3 depositional deep parallel profiles with some across-strike variability. You can already see that what we saw in the thickness is actually translated also in some facies distribution and facies changes. Now I'm going to show you in detail some of these deposits along different parts of the unit. So here you will see in the next slides the correlation panel with the location of each one of the logs and also the location in the map. So you will get oriented in about where in the unit I'm talking about. So Unigi in the proximal settings shows like different packages. At the lower part, we see evidences of sandstone gully fills, so evidences for bypass and erosion. And then in the upper part, we have hummocky cross-stratified sandstones and wave-influenced deposits. So these couple of observations, along many others, suggest that we are looking at the shallow marine topset shelf setting of this unit. As we move down system, a few kilometers down deep along the same panel here, we have that Unigi is changing into much more thelolitic deposits. It's thickening quite a lot, so increasing the thickness. We have absence of wave indicators suggesting that deposition is taking place below storm wave base. We have sigmoidal beds that might suggest some levee deposits, even though we never saw any related channel. But this can also be related to some store side preserved climbing ripples, so high sedimentation rates. We saw a lot of inverse to normal grading, and then some erosive bases, which might suggest a potential river connection. So these all combined, the thickness expansion, the difference in grain sizes, plus the absence of wave reworking, suggest that we might be already looking at some foreset deposits, so in the upper slope. So this suggests that the shelf edge rollover would have been located more or less between these two first localities. As we move on farther to the north and a little bit down deep, we have that unit G here still shows some coarsening, thickening up therolitics, but then in the lower part, we have these continuous thick-bedded erosive sandstones with a lot of mud class and a lot of amalgamation surfaces. And when we try to map it and to follow it with drone, we see that they are essentially very, very discontinuous. And we think that those were suggesting that these deposits were filling some intraslope topography. All these observations combined suggested that we might look at some foreset deposits, but perhaps a little bit farther down system. Finally, in the distal part of the basin, in the upper right corner here, this part here, we see that unit G here in the distal settings shows an abrupt transition from the underlying mudstones with presence of some injections, injectites. So this is how injectites look like in the field. And then we have above this erosive, clean and structureless sandstones that show a subtabular geometry and also these muddy debritic tops. So we interpreted those as hybrid event beds and therefore already basin floor deposits. So suggesting that this part was already into the bottomset setting beyond the base of slope. So combining thickness, paleoccurrence and facies distribution, we came up with this paleogeographic reconstruction of unit G. And in this Mickey Mouse sketch, if you want, in the bottom, we can already see that unit G is documenting an important lateral variability in this Clinothem. In the south, we have this thin and sort of wave-influenced topset, this thick therolitic foreset, and a mud-rich bottomset. Whereas in the upper part, in the north, sorry, we have a step topography with channelized foreset, this intraslope topography filled with sand, and then this basin floor deposits. So when we try to, this is unit G here now, but when we try to upscale this to the general correlation panel of the Lanesburg Depot Center, we see that there is a highly asymmetric sedimentary infill of the basin here. So these are several reconstructions of how the margin has evolved through time. But what I want you guys to see here is that there is a significant eastward reduction and decrease in thickness. And there seems to be a persistent accumulation of sediment to the west, which does suggest that there was potentially some differential regional subsidence from the west to the east. And we're going to talk about this later, because that might be potentially important. So unit G is also documenting a change in the depositional sequences. So below unit G, the sequences are dominated by thick, low-stand deposits, and they contain very thin combined muddy transgressive and high-stand system tracks. Above unit G, these sequences are dominated by shallow marine deposits. They have very little or muddy lowstand system tracks and transgressive system tracks, and then we have a thick sandy highstand. And Unigi seems to be something in between, with sandy highstands, thin transgressive system tracks, and then some variable lowstands that are locally very sandy. So the take-home message, first take-home message, is that the overlying shelf was actually very different than the shelf that was feeding the deep water systems that are below Unigi. So there was indeed a significant change in the type of margin and in the type of shelf that was delivering this sediment. So in summary, what we have in the Karoo Basin is the transition from an erosion to accretion-dominated basin margin. So in the early phase, we have a phase of accommodation limited in the shelf, and then there was efficient bypass and delivery of sand to the basin floor. Then we have a progressive clinoform shallowing, both in gradient and depth, and that leads to the last phase, or to the late phase, with a subsiding shelf that was sequestering the sand and very limited supply to the basin floor. And this was enhanced by these asymmetric subsidence. And the reason why we have these asymmetric subsidence is something that we still are not fully sure. It could be related to some basement configuration, or it could be related to some of the early foreland flexure of this retroarc foreland that was about to start forming. However, we see these patterns in other margins, like in the Po River, for example, or in the Neuquén Basin. But in these cases, this shallowing up of the Clinothems and progressive decrease of sediment delivery to the basin floor is related to the fact that these Clinothems are prograding over basement topography. This is, we don't know if that is the case in the Karoo Basin because we haven't seen evidences for this differential basement, but it is true that the thickness is decreasing to the east. So perhaps there was a little bit of basement configuration here too. Sorry. Right, and now let's move on to the next case study. So classic sequence stratigraphy was trying to study the spatial and temporal distribution of potential reservoir sand bodies in relationship with the accommodation and sediment supply. And then some of these models, like the example we see here, suggest that basin margin progradation occurs when the shoreline arrives to the shelf edge and therefore links this to the accretion of sand. And this is often linked to periods of low accommodation and high supply, like for example during low stands. Not necessarily always the case, but during low stands we have low accommodation, perhaps high supply, and then the systems, the delivery systems make it to the shelf edge. And also then we have the shelf edge rollover trajectory analysis, which I mentioned before, that is also trying to predict sand delivery to the basin. But what about the fine grained systems? No one is really paying a lot of attention to muds. And that is curious, right? Because Clinothems, you will likely agree with me, that are dominated by mud. And not only this, mud fraction is the dominant fraction delivered by rivers. So clay and silt in modern rivers are, in most of cases, dominating the volume of sediment that is delivered. Also, modern studies suggest that modern shelves can be highly energetic and can be progradational. So the question is, what is the role played by fine-grained sediment in basin margin progradation? And then, do mudstones always deposit in quiet conditions? And finally, can we document mud transport and depositional processes in ancient shelves? In order to test this, or to try to answer these questions, we go back to the Karoo Basin. In this case, I'm going to show you examples from both the Tanqua and the Lanesborough Depot Center. And again, because we have this extensive data set with sedimentary logs and borehole data, we can build these correlation panels and we can build these Clinothems. We can show these Clinothems that are actually allowing us to document the transition zones like the shelf edge, for example, and how the shelf edge position has changed through time. So this is the Lainsburg Deposcenter, and this is an amazing work done by George Jones during his PhD. So George was studying the waterfall formation, which is the shallow marine units that are in the upper part of the succession. He documented several of these units, coarsening, thickening upward, separated by flooding surfaces that can be mapped throughout the basin, so parasequences. And he linked all this to a thick high-stand system track. I want you to pay attention to the northern part of the panel where we saw something quite interesting. So this is a zoom of this correlation panel in the north of the Lainsburg Deposcenter. And here you will see where the red circles are. This is showing that the shelf edge rollover was actually quite aggradational when the sandstones were able to meet the shelf edge. So when the sandstones were at the shelf edge, the margin is not prograding that much. But look what happens after a regional transgression. So the black package here, the dark package, is showing a regional transgression, after which some of the sand delivery systems were not able to reach the previous shelf edge, and the pinch outs were in the shelf. And yet the system was able to prograde significantly by the accretion of mud. And that was a very interesting observation. It was a bit counterintuitive because we kind of assumed that the margin was prograding when sandstones arrived to the shelf edge, but that seemed to be not the case in this particular units. So what we did was to go to the field and look at these mudstones to see if we could recognize something. Now you know how difficult it is to work in mudstones in the field. So you barely see, or you expect that you're not going to see much. But we were actually quite surprised because within these siltstones, we could see lots of things. So we saw a lot of subtle bypass features like erosions, incisions. We were still able to break down the stratigraphy because we saw evidences for flooding surfaces and concretionary horizons. A lot of deformations, lumping, soft sediment deformation, suggesting quick deposition. And then evidences for high sedimentation rates, like undulatory bedding that results from these stow-side preserved climbing ripples, which suggest quite high sedimentation rates. And this was all occurring within mudstones. So then we went to another part of the basin, in this case, the Tanqua Deposcenter. This is another correlation panel that is modified from some work done by Richard Weil during his PhD. And Richard also documented a series of Clinothems that were building onto the basin from south to north. And the black line is showing the trajectory of the shelf margin. Thankfully, in the Tanqua Deposcenter, we have a research borehole that was drilled a few years ago, and it's intersecting all the succession, including this area where we thought that we had mudstone deposits close to the reconstructed shelf margin position. So we went to look at the details of the core. And of course, when you look mudstones in core, you see more stuff. We were actually quite surprised because you see a lot of stuff. Here, this is the correlation panel again, showing the trajectory of the shelf edge. This is the research borehole. Here you can see the core lock. And this was the interval of interest. So here we selected a few places in the core, and we did very detailed millimeter to centimeter scale logging. And the surprise was that we saw almost no pure suspension fallout deposits. All these siltstones and towards claystones were dominated by normal inverse grading, suggesting that there was some sustained flows, like, for example, hyperprenite type flows, a lot of internal erosion and bypass, very low bioturbation index, suggesting relatively stressed physicochemical conditions, and a lot of plant debris and mica, suggesting that some of these flows could have potentially be derived by river floods, or at least that the organic matter was actually continental in origin. So combining the outcrop and the core observations, we came up with this conceptual model that tries to summarize some of the processes that we could recognize from these deposits. So from mudstone deposits in the shelf dominated by traction and bypass, some even combined flow deposits due to storm resuspension, and then evidences for flow transformation, like these really nice bipartite beds with very nicely laminated lower parts and very nice debritic tops, suggesting transformations from turbulent to laminar flows. And then eventually evidence for acceleration with these inversely graded deposits with still some bypass and some erosive tops, suggesting that some of the flows make it all the way down into the slope, where we can see these more like nicely graded, normally graded beds. So what are the implications of all this? So mudstone-dominated basin margin successions are important, and I hope you will be convinced by what I have shown you. They are highly heterogeneous in detail. They can be highly heterogeneous, and therefore we need to include fine-grained processes to refine our classic models that are very sand emphasized, especially all our facies models that we show when we study at the university. We know now that multiple processes can provide mud to the shelf edge, river floods, storm resuspension, fluid mud. And therefore, we know now that organic rich mud levels can develop in quite energetic shelves. Now, what is the importance of identifying these mud-dominated shelf edges in subsurface? So here you see an example, a subsurface example from Northwest Australia, where we can see how across strike of the same margin, we have sandy rollovers that are highly aggradational and muddy rollovers that are highly progradational. Now, if we were to apply the clinoform trajectory analysis without knowing the lithologies, we would always predict more sand supply down deep of these highly progradational shelf margins. But that would be completely wrong, because the sandstone-dominated systems are pinching out already quite far up in the shelf. Whereas in here, even though the trajectory is quietly aggradational or rising, the sand delivery systems are very close to the shelf edge and therefore potentially more likely to deposit or to deliver sand to the basin floor. So muddy rollovers are important because they show that there's a potential limitation of trajectory analysis. So here you can see that delivery systems can change laterally from being to the shelf edge to being shelf confined. And yet, the clinoform trajectory can still be highly progradational. So we have to be very careful when we use trajectory analysis alone to predict sand delivery to the basin floor. So now I will briefly talk about a couple of other studies that we've done about this topic. So this is some work that we did in collaboration with Luz Gomes, and this is an example of a shelf edge delta mixed influence, and this is a detailed work we did on a long strike exposure of this delta. And in here we saw evidences that suggest that there is a lot of oversteepening at the shelf edge due to this accumulation of deltaic sandy lobes. And as soon as you stack several of these lobes, some of these high sediment supply can trigger a lot of soft sediment deformation. This soft sediment deformation can lead to a lot of instability. This instability can create some scours, and then some of these can be used as conduits. So we do have a relationship between delta lobe progradation at the shelf edge, oversteepening, deformation, liquefaction, eventually instabilities, and creation of these conduits. And then we move laterally along strike the same margin, and we did another study, the same units. And here we saw something very interesting, is that eventually when you have these lobes that are stacking at the shelf edge and you are oversteepening the shelf edge, this will eventually create a series of gullies, and this series of gullies and instabilities can nucleate and eventually merge into a larger incision that can end up creating a proper shelving-sized canyon. And this can occur without exposing the shelf edge. If you want, it could be even something quite autocyclic related with the oversteepening accumulation of several of these sand bodies, and then liquefaction, instability, and creation of some of these conduits. And we compare this to several subsurface examples, like for example, the Fuji-Einstein Delta in the Gulf of Mexico that was published by Zoltan Silvester. And some of the features that he saw that they document are very similar to some of the things we see in the Karoo as well. Finally, another study that I wanted to show is some of the work done by Grace Cosgrove in the New Jersey margin. Here we did a nice study integrating rollover trajectory and grain character analysis. And this, the idea of this was to test trajectory analysis versus the role of dominant process regime in the shelf. And we had very interesting results. So in some clinoforms that had much more flat trajectory, and therefore we would expect to have sand delivery to the basin floor, we did not find that sand delivery because the shelf was dominated by wave processes. Whereas in other clinothems that were showing a more rising trajectory, because they were dominated by river processes, they were still efficient enough to bring sand to the basin floor. So basically, process regime is an incredibly important factor to consider together with clinoform trajectory analysis. So finally, and I think I'm okay time-wise, some concluding remarks and hopefully some useful take-home message for everyone. Why should we care about all this? Well, from case study 1, we know that Clinothems record the evolution of basin margins and can record major changes in the positional style of these basin margins. The architecture and sediment distribution within these Clinothems can be strongly influenced by basin configuration, but also by seabed topography and slope angle. From case study 2, main take-home message is that shelf edge progradation can occur through mud accretion. So shelf breaks are not always defined by sandstone pinch-outs. And this is, of course, showing that there are risks in trying to identify the shelf break as a proxy to where the sand is. And of course, it implies that using trajectory analysis alone and predict down deep sediment or sand supply can be problematic. From these other studies, we know that oversteepening due to high sediment supply and delta progradation at the shelf edge can promote a lot of deformation, channelization, and degradation in the shelf edge. We know that this degradation can occur without subaerial exposure and that it can migrate, and eventually the interaction between conduits and compensation of delta lobes can create large incisions that basically funnel all the sediment and become really efficient transport pathways. Finally, from the work in New Jersey, we know that process regime is a key factor that controls basin work transfer of sand, and therefore that clinoform trajectory analysis alone is not a reliable predictor if we don't have good control on facies, and in this case, also in grain character. So with this, I wanted to thank the sponsors of all this research, and then I'll take questions from the audience. Thank you very much for your attention.
Thank you so much, Miquel. It's fantastic to see so much data in one presentation, and seeing that whole picture together as well is really wonderful. So thank you so much. And anybody who would like to ask any questions now, please pop them into the chat and tell us where you're messaging from as well, so that we can get a gauge of the global spread of our Seds Onliners. And also, if you are watching this in the as a recording, there is still the opportunity to ask questions. Just go over to the forums and there'll be a dedicated thread where you can go ahead and do that. So we want to keep this conversation going. So please go ahead. And if you think of a question later when you're watching now, of course, the same applies. So so we'll go ahead and start with some of these questions then. They're already coming in, Miquel. Yep. So the first question is from Jonathan Osmond, who asks, could some of the observations noted in the pregrading section of case 2 be related to sourced lithology somehow?
Well, yeah. So of course, our study didn't include petrographic study of these mudstones, but this is of course something very, very interesting that we could consider for the future. In fact, we have now, we are doing a PhD project on mudstones, and Kevin Bullestes, he's published a couple of papers already, and we're trying to characterize the nature of some of these mudstones. So indeed, that could be a very interesting thing to look at. And unfortunately, we haven't done this research in the shelf mudstones, but it's definitely something to consider.
Great. Next question's from Eza Tagliesca, who says, thank you very much for this fantastic talk. I'm just wondering, have you detected and identified any trace fossils?
Well, that is a very good question. And some of the things that were quite striking when we looked at those mudstones is that there was a very, very little, so there were trace fossils and there was evidence for bioturbation, but it was not very specific and it wasn't like very intense. So that suggested us that mudstone deposition was quite energetic and there was a lot of muddy flows arriving to the shelf edge that were preventing some of these sediments to be bioturbated thoroughly. So that was one of the key observations to suggest that this was a highly energetic muddy shelf, basically.
Cool. Next question is from Tim Demko, who asks, was there any evidence for large-scale muddy bed forms from either downslope or along slope processes?
Well, this is a very good question. And unfortunately, as you may be aware, some of these muddy outcrops do not allow for extremely detailed observations in outcrops. So we had to select very carefully the places where we did our logs. And with that, we reconstructed some of the geometries that I'm showing in the correlation panels, but it's extremely hard to see bed forms in the mudstones in the outcrop conditions and in the Karoo. So it's really hard, but of course it's a very interesting question, and I wish I had a better answer, but unfortunately we were not able to document any.
Okay. Next question is from Ricardo, and there are 2 questions, so I'll read them both out, but then we can backtrack if we need to. Wonderful amount of data, Miquel. Great talk. 2 questions. First, what is the difference between the 2 depicenters? What do you mean for depicenters, and are they independent? And secondly, is there potential confusion between what you call heterolithic mudstones and hyperpycnal flow deposits? And can you elaborate on this?
Well, yeah, okay. First of all, depicenters. So depicenters are basically areas of substantial sediment deposition, and they do not necessarily imply that they are not from the same basin. So otherwise I would have called them basins or subbasins eventually. So they are areas where we have a significant accumulation of sediment, and therefore that's why we differentiate these 2 depicenters. But they were forming part of the same basin, and therefore they were likely related. Now, there is a lack of a study that links the 2. So we have this really large correlation panel that is trying to correlate between the 2, but we're still missing this really nice long margin reconstruction. That would be an amazing paper, and yeah, that's in the pipeline, I guess. For the second question, is like heterolithic mudstones don't necessarily have to be related to hyperpycnal flow deposition. So they can just be related to several events, several flow events, several resuspension, or even storm deposits that are able to transport different fractions of sediment, and then the resulting of this is a heterolytic succession. So heterolytic facies don't necessarily link to hyperpycnal flow deposits. I hope I answered the questions.
I think you got it all. Next question is from Domenico Chiarala, who asks, any evidence of internal wave or internal tide in the slope deposits when looking at the cores from Bore Holloway?
Well, that's a very interesting question again. We think the Karoo Basin at the time, we don't have like a great control on which type of paleogeography in general we were looking at, but this has been always thought as an epicontinental sea or a semi-enclosed basin. Therefore, I'm not sure we will be looking for like impressive or really great tidal influence. Having said that, we do see things that might actually look some like tidally influenced structures, but they were not like extremely obvious to our recognition. So that's everything I can say.
Okay. Next question is from Marco Franessi. He says, "Ciao, Miquel. Very nice and clear presentation. Is your facies tract an N number in the hyperpycnal flow spectrum described by Muti and Zavala in the last years? How the argillaceous hybrid beds of the parts of the events may originate?"
Right, so I could have expected this question from Marco, but yes, the answer is yes. So I guess it could be related to the distal track provided by these authors. And in fact, I was thinking about something similar. The point being that if you have a very wide shelf, you also have other processes taking place there, like storm resuspension. So it might not be all necessarily related to one event, but maybe you get the sediment through hyperpycnal flow deposition, and then once you are in the shelf, you get this sediment potentially resuspended, and that's how you manage to bring all this mud this far into the basin, to the shelf edge, and eventually down into the slope. But yes, maybe the origin, the primary flows would have been similar to the ones described by Zavala and Muti.
Great. Our next question is from Gladys Gallot, who says, any quantitative analysis done on the Clinothems and their thickness, steepness, length, etc., that could be used to predict sand reaching the shelf edge?
Yeah, so I gave Stephen a few links to the publications, and there is a little bit of this quantitative analysis. Unfortunately, not a dedicated study on this, but it is a very interesting idea, and we did provide some numbers on gradients potentially, but of course this is from compacted stratigraphy, so we haven't done the compaction of stripping. So that will be the first thing to do before providing reliable numbers. But we did propose some numbers in one of our papers, so I will invite the audience to look at them.
Great, I'll make it available on the website. Cool. So next question is from Valentin Suchat, who says, very good talk, Miquel. Based on everything you've seen, how would long-term climatic changes influence the evolution of your shelf? So migration of the continental hinterground across various climatic belts, for example.
This is an incredibly interesting question. That's something that I didn't touch upon deliberately because it's not like something that we have a very clear idea. But because the Permian is registering the change from ice house to greenhouse conditions, we think that perhaps some of this absence of really clear sequence boundaries in the shelf, for example, might be related to greenhouse sea level variations, which are, they have less amplitude, perhaps higher frequency, but less amplitude. And that could be a reason behind the absence of some of these, for example, sequence boundaries in the shelf. So this would be the product of this sort of climatic variability in the long term of the succession. Yeah.
Okay. Cool. So we're getting quite a few thank yous coming through. So on a similar note then, while we wait for the next question, I'll ask a question about what you were asking with the modern systems that have been studied with the sediment coming down rivers.
Mm-hmm.
Do you think that there could be any influence from humans that is potentially impacting the data that's being
Well,
used?
absolutely. Some of the modern day sort of sediment that is delivered by rivers is influenced by the by anthropogenic influence of these sort of dams, hydroelectric power plants, things like that. And of course, this is changing a bit the numbers, but I believe some of the rivers might actually not show that much. So not all the examples are related to this. And therefore, I still believe, because when you look at seismic sections of Clinothems, like a really huge percent of all this sediment is mud anyway. So I think we can quite confidently say that mud is the dominant fraction of sediment delivered. And it's been like this, at least for most of the Clinothem successions that we study.
Great. Well, thank you so much for answering all of those questions, and thank you very much to our audience. And I have to give a shout out to the Strat community who came in vast numbers for your wonderful questions too. So, and thank you again, Miquel, for such a lovely talk. Very clear and wonderful data. So we hope to see you all again next week for our talk, A Guide to Life, Earth, Life and Terrestrial Carbonates for the Intergalactic Sedimentologist. So if anyone's planning to get on that one-way trip to Mars, I think this is a must-have talk to do about. And that's going to be from Alex Brazier at the University of Aberdeen. In the meantime, if you can't get enough of sedimentology, come along to our coffee breaks and have a chat about sediments and everything. You know, cannot predict what comes up in these coffee breaks at all. So yeah, come along, say hi. And with that, thank you all again, and we'll see you next week, if not before.
Thank you.
Cheers.